Hi guys. Okay, so let me ask you a question. First of all, have you ever wondered why is it that certain substances get heated up quickly and why is it that certain substances take very long to heat up? On the other hand, why is it certain substances cool down quickly whereas other substances take very long to cool down? Because of the differences in the properties of the substances, for example, water and the sand, which is made up of silica, we enjoy ambient temperatures on the coasts. Water takes very long to heat up and it takes very, very long to cool down also. On the other hand, silica gets heated up faster and cools down faster as well. So this is the reason why during the daytime we have nice cool breeze on the coastal cities. Whereas on the other hand, at night time, we have warm breeze when it's not, we don't want things to be very cold at night time. So we enjoy the warm weather at night time. And then there is much more to it, but where we are looking only at the properties of the substances and their ability to absorb the heat and to liberate the heat. But before we get further, let's just focus on the heat. Heat is a form of energy, right? It's not something that you can hold in your hand and you say, hey, I have this much amount of heat. There's no way we can do that. So we have a system in which we have a temperature and the difference in the temperature, which tells us like, okay, there has been either a gain of heat or a loss of heat. But how do we actually quantify heat? How do we know how much of the heat we have? For that, we have certain formulas which are based on certain relationships. So we are going to study in this video about the heat capacity, molar heat capacity, specific heat capacity of substances. Okay, so let's look at it. Okay, so as you can see on the screen, we are going to be talking about a number of phenomena that relate to the heat, the temperature, and the energy, and then the properties of the substances and so forth. So first, try to understand what is thermal energy. Thermal energy, as the name says, thermal means it relates to heat. So when you heat a substance, the molecules or the particles inside that substance, they absorb the heat and they become agitated or they start the vibrations. So anytime the temperature is high, the kinetic energy is going to increase. When the temperature goes down, the kinetic energy becomes lower. So in other words, at a higher temperature, the thermal energy increases, and at a lower temperature, the thermal energy goes down. Okay, so this is the kinetic energy that is directly proportional to the increase or decrease in the temperature. Okay, next, let's look at the flow of heat. Yes, the heat flows from a higher temperature to a lower temperature. So as you can see, the red colored particles are the ones that have a high temperature. The blue ones have a lower temperature. So when you mix the two, the heat is going to flow from a higher temperature, the red ones, to the blue ones, the lower temperature. And this continues to happen till the heat it becomes equalized. In other words, the temperature becomes the same on the hot and the cold side. So this is the reason why you see that if you take um, a spoon, which is a steel spoon, and you place it somewhere near the, like something hot, the spoon gets hot, even though the spoon is not directly, you know, uh, touching it. One end of the spoon may be inside the hot soup, let's say, but the other end of the spoon is outside. So the other end of the spoon that is not directly in the hot soup still becomes warm because of the heat is transferred, from a hot end to the colder end. Okay, so there are two processes. One is the exothermic process and the other is the endothermic process. Exothermic process, whether it's a physical process or a chemical process, releases heat. Okay, an endothermic process absorbs heat. So these are the two things we are going to be looking more into the details, but let's look at the units of heat. The units of heat are in calories with a small c. But there is a nutritional calorie which is related to the food. That one is with a capital C. And the relationship between the food calorie and our normal ordinary general, heat calorie, that is 1000 small calorie is going to make one nutritional calorie, the big one. Okay, so that's one thing. Second thing is one small calorie. Now we're going to focus only on the small calories. So one small calorie is equal to 4.184 joules, and 1 kilocalorie is equal to 1000 calories. Okay, so what is a calorie? Calorie is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So now what are we doing here? We are trying to see how much of the heat is being absorbed by this substance and what is the value of that heat. Okay, so that heat is now being measured and quantified. So what is our measuring device? As I mentioned, thermometer. So the the increase in temperature, so this piece right here I have shown is the thermometer. Thermometer. So thermometer records the heat change, right? So the increase in the heat, obviously the meniscus moves up, but the decrease in heat is going to bring the reading down. So whatever the amount of heat is being absorbed or released, you can measure by the change in temperature. So that's one thing very general regarding the calorie. Now, what is the heat capacity? Now, heat capacity depends upon the amount of substance. Now, you imagine you have a glass of water and you have a pan of water, and then there is water that is in the ocean. Depending upon the amount, yes, the heat capacity differs. So the heat capacity is the amount of heat that is absorbed or released by a substance when it experiences a change in temperature by 1 degree Celsius, and the formula is Q over delta T. Q is the amount of heat, delta T is a change in temperature, and J is the joules over degree Celsius. Now just imagine this. You are working with two pans, okay? Pans of iron, okay? And these are iron pans. Now these iron pans have certain capacity to absorb heat, and that depends on their amount. So heat capacity is an extensive property. In other words, it depends on the amount. Smaller can is going to obviously get heated up quickly. A bigger can, a larger can, is going to take longer to heat. So let us say the change in temperature is 50 degrees Celsius. So the first one, a smaller can, absorbed 18,140 joules of heat. So the heat capacity of a smaller can comes out to be 363 joules per degree Celsius. On the other hand, if you have a larger can, that one absorbed 90,700 joules of heat, and the change in temperature was 50 degrees Celsius. So the heat capacity of the larger fan is 1,814 joules per degree Celsius. Again, this depends on the amount. But there's another property of the substance, which is the specific heat capacity. That is also represented as SH or SC. So normally we use specific heat capacity for the substances because here's the thing, it does not depend on the amount, whether you have a small pan or you have a large pan, because this property is the intensive property. An intensive property, it depends on the kind of the substance absorbing or releasing the heat. Okay, so it has nothing to do with whether it's big or small. It is the nature, what is it made up of? That is specific heat. So that is why the name says specific heat. So it is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So Q is the amount of heat, M is the mass, delta T is a change in temperature, and C is that specific heat. So I'm going to just write down here, Q is the heat, M is the mass of the substance, delta T is the change in temperature, okay? And now we see that the C stands for specific heat. So specific heat. Okay, specific heat is the amount of heat that was absorbed in the case of a small pan, that was 18,140 joules, over the mass of the small pan, which is 808 grams, times the change in temperature. So this comes out to be 0.449 joules per gram degree Celsius. Now look at the iron. Iron, which is, look at the larger can, which is also made up of iron. The amount of heat it absorbed because it's large was 90,700 joules. And the weight is also more. The weight is 40 grams, right? And change in temperature is 50. So here also we see that the specific heat comes out to be 0.449 joules per gram degree Celsius. So specific heat, you can even use this specific heat to determine the identity of the substance. So just like you have the specific heat, there is the molar heat capacity also. Now molar heat, it just depends. The molar is the units or the amount of heat that is required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So instead of 1 gram, it is 1 mole. Okay, so we are going to be looking at into this molar heat capacity later. But look at some of the sample problems now that are given to us. So here we see that we are given a mass of a substance which is 8.1 into 10 to the power 2. Okay, 8.1 into 10 to the power 2, or roughly it is like 800 grams. Okay, so this is the 800 grams of water. And this water, we are heating it. Okay, and we are trying to measure, in this case, we are trying to measure the value of um, the amount of heat that the amount of heat that the water had absorbed. Okay, so the initial temperature of water was 21 degrees Celsius. The final temperature is 85 degrees Celsius. C is the specific heat capacity, which is known value. So this is the specific heat capacity of water. And this is known. This value is already known. Okay. All right. So you find the value of the amount of heat that the water had absorbed. 800 grams of water had absorbed that brought the change in temperature from 21 to 85. So what is the formula that we are going to use? First of all, in this case, you're always going to write down the formula. Now, here's an interesting piece. So here is your, this piece, this formula, Q C is equal to Q over MC delta T has been rearranged, and now we have this formula, which is Q is equal to M times C times delta T. So we are given the mass, which is 800 grams. We know the value of the specific heat of water, which is 4.184, okay, joules per grams degree Celsius, into the change in temperature, which is T final, which is 85 degrees Celsius, minus the 20 degrees Celsius, which is 20 or 21. Oh, okay, it was, sorry, I wrote this wrong. This initially was 20 only. Okay, so 20, okay, here. So 20 degrees Celsius, okay? So now we are going to do the math. Here we have 800 grams and 800 grams cancel out. So let's just do it with the red color. Okay, 800 grams cancel out, right? Or, sorry, let's make it more conspicuous. Okay, 8 and 8 grams cancel out. And we have Celsius and Celsius cancel out. That one also is going to be in Celsius. Sorry, degree Celsius. So this is also going to cancel out. And we are then left with just the unit of joules. So we see that we have 800 times 4.184 joules times, that is 65 degrees Celsius. Okay, and that gives you a total of 210,000 joules. So this is the amount of heat that was needed to bring that temperature from 20 to 85 degrees Celsius. Okay, now sometimes the question can be asked, find out the value of Q in kilojoules. So 1 joule is equal to, 1 joules, sorry, 1000 joules is equal to 1000 joules is equal to 1 kilojoules. So in other words, 210 times 000 into 1 kilojoule over 1000 joules. Remember that this is going to be the conversion factor, 1 kilojoule over 1000 joules. Okay, so now you are going to get rid of, sorry, this one I didn't put this joules here. So now you are going to cancel the joules and the joules, and you are left with the 210 kilojoules as the value of the amount of heat. Okay, let's look at it another example in which you are given the mass of 348 grams of a substance. Initial temperature 22.4, final temperature 43. You're given the heat 66.40 joule, and you want to find out the specific heat of this particular metal. So once again, we are going to write down the formula always. Q is equal to M times C times delta T. Okay, so here we have to do some algebraic conversions because this is the term that we need to find. Okay, so we are going to put it like this. C is equal to Q over M times delta T. So now just try to just put in the numbers. So 6640, that's the joules over the mass. And how much is the mass given? 348 grams times the change in temperature. So this is, we need to do this, 43.6 degrees Celsius minus 22.4 degrees Celsius. And what do you get here? You're going to get 21.2 degrees Celsius. So that's the number you're going to bring here, 21.2 degrees Celsius. And after doing this, we get 0.900 joules over grams degree Celsius. Okay, so this is the specific heat capacity of this substance. Now the question can be asked, what is this particular substance? What is the identity of the substance? So here, very important, you will compare it with the given tables that have the specific heat capacity. So comparison with other substances in or given in the table, okay, or sample or something, okay. So then that's going to give you. So here there's going to be generally these appendix, you know, has the appendix in the books will have the specific heats of other substances, specific heat of other substances. So just compare it from there, and then from there you can decipher the identity of this unknown substance. So you found the specific heat capacity, and that's how you also determine the identity of the substance. Okay, so I hope that was easy, and thank you for watching. Bye bye.